This program is brought to you by the University of California, Davis on iTunes U. For more information, please visit us at itunes.ucdavis.edu.
Hello, lecture number 2 today. And tonight I want to talk about one of the most important curve schemes that exists, and that is the scheme of Bezie curves. Now, before I come to that, I would like to talk a little bit about notation and how we denote things, points, lines, line segments, and so forth. So let's first start a little bit about notation. And the important things that we talk about are, of course, points, lines, and that's pretty much it. All you need to understand in this class are points and lines, nothing else. So we have a bunch of points, and a point, P, will usually be written as a column with two components, right? XY or XYZ, if it's in 3 dimensions. XY. And then we need the concept of line segments. Line segments would mean there is a line going from one point to the other, and say this is point P0 and this is point P1. Then from 0 to 1, so there is a direction also involved there. From P0 to P1, 2 points, you connect them, there is a difference vector there. So we also need to talk about vectors and how do we write them. Difference vector. And we would write this vector, V, in this case, as 0.1 minus 0.2, 0, and that would be just component-wise subtraction, right? x1 minus x0 and y1 minus y0. Sometimes, and only in exceptional cases, I may put a little arrow on top of V to indicate that's really a vector, but typically the context will tell you when it's a point and when it's a vector. Okay? So this is notation. This is all that we need to understand in this class. How we write a point and how we write a vector. So I use these strange boldface characters, right, to indicate that something has multiple components. So when I do not make anything in boldface, like this xy, then it's just one value. Whenever I make things with these boldface characters, that indicates that this thing or these creatures have multiple components, right, namely x, y, and z in 3 dimensions. Now, there's only one thing, one operation that we need to understand in this class, and that is linear interpolation. What is a line? How do I represent a line? And how do I move along on a line? That's it. That's the only operation that we really need to understand and appreciate. So the other important thing here is this was a precursor number 1. So precursor number 2 is linear interpolation. Linear interpolation. That's all we need to understand in this class. And we apply it over and over again. What is linear interpolation? There are 2 words, right? Linear and interpolation. So what does it refer to? Anyone?
Interpolating along a line.
Interpolating along a line. So you say ideas. So you say there is a line, okay? And linear interpolation. What is linear here? This thing is linear. It's a line, right? What do you interpolate?
You don't have actual points, you have like dots, and so you have to make up the line with a bunch of dots that aren't necessarily connected.
So there's a bunch of dots on this line, and so these points all lie on a line, and what do you interpolate?
But they're made of squares, not really like perfect sized dots.
The circles are squares?
Like pixels.
Pixels? Okay, you think in terms of computer graphics. Right? So you also worry about how to map this to a computer graphics world, right? We don't worry about this in this class. How to do that and turn on these pixels. And these are the representations of lines on a computer screen. And we stop here. We assume that we are able to actually draw these lines smoothly. So the computer graphics is doing something with this and breaking it down into pixels. We don't worry about that. So, but you're right, essentially. So let me say what linear interpolation really refers to. So there is a line. I start with a simple case, and we call this line x. And I designate two positions on this line, and I call it x0, and I call it x1. And at these two locations, I have two values, right? Function value 1, function value 2. Oh, okay. Or I call it function value 0, because it's f0, and I call this function value 1 for x1. And then I fit a line to these 2 points. That's linear interpolation. Huh? I interpolate these two values linearly by a line. Huh? Linear interpolation. Now, there's a formula for that, of course. If I can do this geometrically, then there's a formula, and here is my f-axis, f of x. And now I can say, what is f of x? F of x is the equation for this line, and it's very simple. It is 1 minus x0 times the left value, f0, plus x. It is 1 minus x times f0 plus x times f1. Is this formula correct? Is this formula the formula for this line? How do you find out? Well, you plug in x0 and x1, and you want to get back the values f0 and f1. Do you do that? Does the formula do that? Well, when you plug x0 in there, you say x0 in a specific case, and I should start with that. In a specific case, the simplest case, I call these values 0 and 1. Okay. So 1 minus x times f0 plus x times f1. So I plug 0 in there. What do I get? I get 1 minus 0 is 1 times f0 gives f0 plus 0 times f1. So it's really f0. What happens when I plug 1 in there? It's 1 minus 1. It's 0. 0 times f0 plus 1 times f1. That is f1. So at the right end, at 1, it interpolates f1. So that's the equation of the line. Now, and I was jumping ahead already. I said, not always do you have these values given at values 0 and 1, but at arbitrary values, x0 and x1. So this formula changes, right? So more general, the more general case is the case that I actually had on the board already. So you have two values, one on the left, one on the right. These values are given on the x-axis. Here's your function axis, f of x, and you have arbitrary locations. The first one, x0, and the second one, x1. And at these locations, you have function values, and I call them f0 and f1. And again, you want to interpolate them linearly by a line. Now these values, x0 and x1, are arbitrary, and the formula becomes arbitrary, becomes more general. What is it? And I'll just give you the result, and then we check that it's correct. So fx is something times the value on the left, f0, plus something times the value at the other end, f1. What do we have to do? We have to divide by the length of this interval here, x1 minus x0, x1 minus x0, divide by x1 minus x0. And then in the numerator, what do we have to put in the numerator? Here we have to put x1 minus x, and here we have to put x minus x0. And now we have to convince ourselves that this formula is indeed correct. How do we check that? Well, we have to check at these two ends, right? Whether we get these values back when we plug x0 and x1 into that formula. That's it. So we plug x0 into the formula. What do we get? x1 minus x0 divided by x1 minus x0 is 1. 1 times f0. Now I plug x0 in here. It's x0 minus x0 is 0. So it is f0 plus 0 gives f0 at the left end. Now what happens when I plug x1 into that formula? I get x1 minus x1 is 0. So that is all 0. Plus x1 minus x0 divided by x1 minus x0, that's 1. 1 times f1, so I get the right value of 1. So that's correct. And for any value x in between, I get a value that lies on this line. All these happy values lying somewhere between the end values. That's linear interpolation. That's the only form of interpolation we need to understand. Okay? So if I can interpolate with one line, I can also interpolate with multiple lines, right? can do that. And that is the essential idea of Bezier curves and the so-called Casteljau algorithm. And the whole concept is called repeated linear interpolation. Repeated linear interpolation. Let's see, what do I mean by that? Repeated linear interpolation. Actually, first I should go to a more general setting and say how we go from the setting where we have an x-axis and a function axis to the setting of just two-dimensional space. If I just give you points in xy space and there is no longer an f, okay, it is just xy. I just give you 2 points in xy space, and I call this first point P0, and I call the second point P1, and here is the direction of that line. The line segment is this, right? The entire line is infinite, and here is a line segment that's finite. And I say there is a so-called parameter t for time, and I take a chunk of this t line from 0 seconds to 1 second, and I want to take this line and map it to this line, which is given by 2 points in space. What is the mapping? So now this line is a line p depending on this parameter t, and whenever I plug the value 0 in there, I want to get p0, and when I plug the value 1 in there, I want to get 0.1. Okay, so I want to have this correspondence. 0 maps to p0, and 1 maps to p1. Okay, how do I do that? This is a more general setting, right? Because now I use these boldface characters, meaning these are points, xy, components, are there to represent both of them, and I have a line. So now the equation is the very same as over there, and I say it is 1 minus t times the first point, p0, plus t times the right point, or the second point, p1. This is the very same equation that we have over there, except that now we have an x of t and a y of t. Okay? Component function. So here is an x of t component, and here is a y of t component. Okay. Now again, not always do you have the values 0 and 1 associated with the two endpoints, but arbitrary values. So the formula then generalizes in the same way it generalizes here. Okay. So the more general case looks like this. I give you 2 points. I give you a line. Okay. I call this point P0. I call this point P1. And I have my so-called parameter line. This is the parameter. Now, going from an arbitrary value T0 to an arbitrary value T1. And so these T values map to P0 and P1. And this line, any point on the line now, is given by some equation that relates these parameters, the points, and then the variable t to each other. And so the general formula would be any point depending on t is something times the first point, something times P0, plus something times the second point, P1. What do? I do the same trick that I did over here, right? I first normalize by the length of this parameter interval. I divide by T1 minus T0, T1 minus T0. And in the numerator, I again follow the same principle. So it's T1 minus T, T1 minus T, and here it is T minus T1. And that should be the formula for arbitrary linear interpolation of 2 points. Okay. How do you verify that the formula is correct? Again, you just plug the values t0 and t1 into the formula, and you should get back
T minus T0.
t minus t0. Exactly. Yes, good point. That's it. So you plug the two values in there, and you should get the two endpoints back. That's it. This is the only interpolation method we need to understand here. We don't go to parabolas and quadratic functions and cubic functions. Everything will be just this. Do you believe me? Gary? You believe me? So if we only do lines, how can we represent something that is smooth and curved? Ultimately, everything is just pixels in computer graphics, right? So ultimately, everything is just a bunch of illuminated squares on the screen. That's true, but we don't worry about that. We assume that we can do mathematically ideal representations, right? So how do we combine that? Lines, and then we want to go to parabolas, right? Parabolic shapes and cubic shapes and all of that. How is that related? Well, that is related through repeated linear interpolation. So, and now, you don't have to copy this. This is just to motivate. If I have one line, obviously this line interpolates two endpoints. This line segment is between two endpoints. And when I linear interpolate between these 2 points, I can generate a bunch of points that lie in between, right? That is using one line segment. I can go from one line segment to two line segments. A first line segment and a second line segment. I have two, and I can do linear interpolation on each of those line segments. So I can interpolate the first one at 1/2 and the second one at 1/2, and then I can connect these points again. I have one line segment, and I can linear interpolate on that line segment at the middle, and I get a point there. Okay, so I did that. If I do this for different values of t, here I did it for 1/2, right? 0, 1/2, 1, 0, 1/2, 1. I do that for multiple points. Ultimately, I can generate a bunch of points which lie on a parabola. But I can avoid ever having to worry about a quadratic equation. I can just use this concept of repeated linear interpolation, first, second, third time, to generate a bunch of points that happen to lie on a parabola. But I never deal with a quadratic equation explicitly. Okay, so now I talk about repeated linear interpolation. And that leads to Bezie curves. Bezie curves. Bezie curves and repeated linear interpolation. I do a very simple example, and once we understand fully and appreciate this first example, we can do it for any other example. So, simple example. We take two lines, or line segments, right? It's the difference between the line and the line segment, right, Samuel? The line is infinite, the line segment is finite. So, I make some circles here, and I give these points some names, and I call this one Mr. A, this is Mr. B, and this is Mr. C, A, B, C. I need a parameter, right? This time, this is time parameter t, and I restrict myself to just using this interval 0 to 1. And now I want to put a particular value there. Maybe it looks like 2/3 or so. And I will apply repeated linear interpolation according to the formula on the other side, according to the upper formula on that board. So I apply that to the first line segment, and I will get a point here. And I apply this linear interpolation formula to this line segment, and I get this point. Okay, so what have I done? Mathematically, I have done this. I have said I construct a new point, D, this guy, and then another new point, E, which are linear interpolations of A and B and C, respectively. And I can write this down using the formula over there. So I can say the point D is just 1 minus T times A plus T times B. The other point that I introduced, the point E, is 1 minus T times B plus T times C. Okay, that's what I did. Now I do repeated linear interpolation. What do I repeat? Well, these intermediate points I connect and have a new line segment. And again, I do linear interpolation on this line segment using the same value here to get this point. And I call this point F. Okay, so F is given as linear interpolation by linear interpolation of D and E. So F is 1 minus T times D plus T times E. Okay. Also, very interesting, is the geometry that's implied there, but I do not do that yet. First, I will multiply this out. For D, I have this expression. For E, I have that expression, so I can plug that in, right? And see what this really is. So this is really, I plug D and E in, and I get this is 1 minus T squared times A plus 2 times 1 minus T times B plus T squared times C. That's what this value F is. And all of a sudden, you see that we are dealing actually with quadratic terms, right? So there's this power of 2 there. Meaning that we are really dealing with a parabola there. Somewhere there's a parabola, even though we just computed one particular point on it. How do we get the whole parabola? The whole parabola we get, or points on it, by plugging in different values for t. When you plug in different values for t using that formula, you will get a bunch of different points on the parabola, which when you render it, you just connect by line segments, right? Another important thing is the geometry. This is the geometry. And the important part is these ratios. So here's a ratio from 0 to t and from t to 1. So that ratio is t to 1 minus t. And this ratio is mapped onto these line segments, right? That's the way I've drawn it. So you have the same ratio here, t to 1 minus t. You have the ratio here, t to 1 minus t. And you have the same ratio here, t to 1 minus t. So in a sense, you take this configuration, 0, t, 1, and you map it here, 0, t, 1, 0, t, 1, and 0, t, 1. That's what I do. And I only applied the same mechanism, linear interpolation, multiple times. And then I dared to multiply it out at the end, right? Which I don't really have to do. I'm done here, right? Just multiply it out. So that's all what we need, all that we need. We need linear interpolation, nothing more. How do you render the entire curve? Well, again, you render the entire curve by using multiple values for t. Then you get multiple points, right, on the curve, which for rendering you would connect simply by line segment. And when you use an infinite number of t values, you get an infinite number of points on this polynomial, and it looks like a parabola. It will be a parabola because it is a parabola, right? It's a quadratic curve. So far so good. So there is geometry, there are formulas, but we are computer scientists, right? Or we think in terms of computer science terms. So what do we need to do? We need to write a program, right? All of this has to become a program. What's a program? What should the program do? Okay. This is related to your first assignment. First assignment should do the following. User will click these circle points. Click, click, click. These circle points will be connected by line segments. And then you say, render curve. And render curve should produce a picture that looks like that. Huh? This is an infinite number of points on the particular parabola, which you do not do. You would only render maybe 100 points or 1,000 points on that, and then use little line segments to connect them, correct? Okay, so then what are the operations that the user should be able to do on the original circles? Well, you add circles, you delete a circle, or you move a circle around, and when you do that, the shape of the curve will follow, right? Will also change. Okay, so what is the algorithm that we actually use to code this up in C, C++, or Fortran, or Java, or Python, whatever you like to do? What is the code? You only have to understand the geometry, which is most beautiful. This picture tells the whole story. Right? Everything is there. Well, you can think more formally if you like to think in terms of formulas. This is a story told in the same in an equivalent way. But now we have to think in terms of arranging it so that it lends itself to an algorithm. All right, so now comes what is called the Casteljau algorithm. Casteljau algorithm. I use the same example that I had on the board, but I use slightly different names for the variables. Okay. Okay, so I start with the geometry. Okay, geometry. The geometry is this. I have points. I call these points B points, B0, B1, B2. And then I have this value T, which was a value between 0 and 1 particular value here. And then I constructed intermediate points using these ratios. So I mapped this ratio configuration to this line to get a point lying there. I use this ratio configuration, right, this ratio, and map it here to get that point. And then I connect these intermediate points by a new line segment. And again, I take this ratio configuration and map it here, and I get that point there, which is a point on the curve that we want to render. Now I give all these points that I've constructed also a superscript. The original points are of generation 0. Huh? So they are B0, 0, B1, 0, B2, 0. Okay, so how do we name the points of the next generation, the children, in a sense? So you could say this is point B0, 1, right, of generation 1, and this is point B1, 1. So this point then is of generation 2, and you call it point B02. Now, at least you have some kind of consistent naming, right, or indexing. You always start from 0 and you go forward, and then you consider where you are in the generation. The original points have a superscript of 0, and then it goes forward 1, 2, 3, 4, 5, and so forth. What I've done there, I can now put into a triangular scheme. Triangular scheme. Okay, now I think more in terms of the algorithm, the method that I want to actually program. I just arrange these points in a scheme. So here is B0, 0, here is point B1, 0, here is point B2, 0. And then what did I do, I use the first and the second point to generate this point. Okay, only these 2 points are needed to generate that one. So these 2 points generate point B01. That's indicated by that. These 2 points are used to generate this one. So B10 and B20 generate B11. And B01 and B11 generate B02. So that follows here in that scheme. So here is B02. This is just a structural way of thinking of what we are doing. Okay. What do I do? I always have to multiply the upper one by 1 minus t and the lower one by t and add the results to get the next point. Right? That is always the operation that I do. Give me 2 points, give me a value of t, and interpolate the points to get a point in between. So B01 is 1 minus t times B00 plus t times B10. That's what that means. And I do that all over the place. All over the place, you do the same linear interpolation. Plus, this one is times 1 minus t, and this one is times t, and then you add the results. Okay. So this is an example for n. N is 2 here, right? 0, 1, 2. For n equals 2, a quadratic curve. But now I can do this for arbitrary curves. I can also go from B0, B1, B2 to up to B10 or B100, right? And then this triangular scheme will just grow. There will be more columns and more rows. It doesn't scare us, but as computer scientists, we use arrays. This is probably an array structure, right? There's a loop somewhere. There's a loop, right? I go first column, second column, third column, and then I do something row by row. So there is a double loop to evaluate this, right? So that's the next thing we have to see. How does the triangular scheme lend itself to a natural algorithm, which will become very simple? So from triangular scheme to algorithm, from triangular scheme to the Casteljau algorithm. That's the keyword. I take the scheme that are over there, and now I draw it in the general sense. So always I have a first point, B0, then there's a B1, and the last point will be some point, Bn, correct? These points are of the first generation, and they have a superscript of 0. Okay? I always will take 2 points to define the next one, a point of the next generation. So this point here will be point 1, n minus 1. And I will combine and combine, I will combine and combine, and ultimately the last point will be B. What is it? It will be of generation n, and it's 0. It is the same scheme over there, except that I write it for an arbitrary number, n of control points, right? I just make that scheme bigger. More lines, more rows, more columns. Okay. Now where's the algorithm? The algorithm. What is given for the algorithm? We need to know what is the input, right? Given is a set of these original points, the original control points, B0, 0, up to Bn, 0, and the parameter value t. We want to evaluate the curve for some value t, right? T. and t for our purposes should be between 0 and 1. So, and now, what does the de Casteljau algorithm do? I have lines or rows and I have columns, right? So this, what is this? I can say j equals, j is my upper index, so here j is 0, here it is 1, and at the end, j is n. Okay, so I have to do something for all these j values. For j from 1 up to n, do something, compute all these entries in that particular column. So I have to say, first loop, outer loop, for j from 1 to n, do something. Okay, now I need to compute all the entries in a particular column. Okay, so I have to say for I from 0 up to n minus j, I from 0 to n minus j, do, it's the inner loop. What do I do? In the inner loop, I have to execute this particular step. Given two values, compute the next one from the two values. So it's always this guy multiplied by minus t, this guy multiplied by t, and adding the results. Okay? And now you have to think in terms of the arbitrary I and j indices, right? This is the I, and this is the j. Or, putting it generally, so you have b, I, j. Okay, bij depends on 2 points of the previous generation, right? So it has to be 1 minus t times a point b of previous generation, j minus 1, plus t times point of previous generation, j minus 1. And what are the lower indices? So this was 0, so this is the I, 0, 0, and 0 goes with 1, so it is I and I plus 1, right? So this has to be b sub I, and this has to be bi plus 1. That's the essential formula. And that's all there is to it. This is a repeated interpolation expressed in terms of a double loop, which is based on this picture, right? The triangular scheme. It's all the same. So, and at the end, you have to return the result. And I just say return. Return. This is the result. Return b0n. And that's the point. That's the point 0.4 t value. Now we will do a bunch of examples, so it becomes very intuitive and you understand this. Maybe one example with numbers, make it very simple. Example. And we also will talk about the computational cost for doing this algorithm. Is it expensive to do that? Is it not? How long will it take? How long do you have to wait to draw a curve? Example, I give us 4 control points. Okay, this one, this one, this one, this one. And so this is B1, B0, and I give them concrete numbers. This is 0.00, this is 0.04, this is point B1, B2, and it has components 4, 4, and this point is point B3, and its coordinates are 4 and 0. And I would like to evaluate the curve t the curve runs between 0 and 1. I would like to evaluate it for the midpoint, for 1/2. Where is the point on the curve? 1/2. How do I do that? I do repeated linear interpolation. All I do is repeated linear interpolation. So I map this ratio 1/2 to 1/2 onto these line segments, right? And I do it over and over again until I no longer can do it, until I'm done. I'm running out of lines. Okay? Which is the first intermediate point that I get when I do this? I interpolate on this line segment linearly, and which point do I get? This is 0, 0, this is 0, 4, so I get 0, 2. Okay, so the first intermediate point will be this guy, and it has a name. We don't care so much about the name in this case, just want to do the concrete example with numbers, so this would be 0, 2, right? And that has some name. The next point would have coordinates what? This is 0, 4, this is 4, 4, so the point in the middle is 2, 4. Okay, so get this intermediate point with coordinates 2, 4. And the other point here has coordinates what? 4, 4, and 4, 0. So the midpoint is 4, 2. I get this point. Okay. Now, repeated linear interpolation, where the new line segment? The new line segments are the connectors, the connecting line segments of these new points. Okay, now I do this again. I evaluate. You can call it evaluation. I evaluate these line segments for 1/2. What do I get? I get this point, and I get this point. Okay. What are the coordinates? This is 0, 2, and this is 2, 4. So that point is 1, 3 is the average, right? Or the midpoint, 1, 3. And this point is, this is 2, 4, this is 4, 2. So that point is 3, 3. Okay. Repeated linear interpolation. What do? I take the two intermediate points, I connect them by a line, that's the linear part, and I compute the midpoint. What is the midpoint of those? The midpoint of 1, 3, and 3, 3 is 2, 3. Yes, that's it. So that's the point on the curve when I evaluate the curve for 1/2. Now I can do the same game for using different values of t, right? If I use a bunch of values, ultimately I will get a gazillion points on the curve. So when you use more, then you will get more points on the curve. And ultimately you would use a resolution, choose a resolution of 100 or 1,000. And then you connect all these points on the curve by little line segments, and on the screen it will look smooth, even though it's just a bunch of line segments. Or further down, it's just a bunch of pixels, right? So this is an example. Now we do a little bit more control points. So I can do this for 2 line segments, right? If I evaluate this for 1/2, 1/2, 1/2, new line, 1/2, I get a point. The curve will look like that. If I can do it for 2, I can do it for 3 line segments, right? 3 line segments. If I evaluate it for 1/2, I get midpoint, midpoint, midpoint. I connect these. New midpoint, connect, new midpoint. There's a point on the curve. Can I do it for more? I can also do it for 1, 2, 3, 4 control points. And I want to evaluate this polygon. You evaluate a polygon in a sense, right? I evaluate the polygon for 1/2. So what happens? This is very simple. 1/2, 1/2, 1/2, 1/2. I connect these new intermediate points by line segments, linear, and I do the same game again. I interpolate for 1/2, meaning taking the midpoint. I have new intermediate points. I take these points, connect them. I have 2. I do the same game again, evaluate for 1/2, and here's my last line segment. I'm running out now, and here's the point on the curve. This is 1 point on the curve, right? Samuel, and now I have to use different values for t, and I would get different points on the curve. And then the ultimate curve would look like that. So this is just one particular point on this curve. When I evaluate it for 1/4, I would get this point. When I evaluate it for 3/4, I would get that one. When I evaluate it for 0, I get the first point. When I evaluate it for 1, I get the last point. So, can I do it for more? Can I do it for more? Of course, you can do this for 1,000 initial control points, right? Let's do it one more time. 1, 2, 3, 4, 5, 6, 7. Okay? Huh? Does it become more expensive to evaluate it now? Maybe it does. You have to think about that too. I want to evaluate this for 1/2. If I do that, midpoint, 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 and I connect these midpoints, I get a new polygon. The length of these polygons always shrinks by 1 in each step, right? I lose one line segment every time. Take the midpoint, take the midpoint, take the midpoint, 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 midpoint. I connect these midpoints by line segments again. Okay, I can play the game again. Take the midpoint, 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 and connect. Connect, connect. I can do it again. Midpoint, 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 midpoint. I connect, midpoint, midpoint, and midpoint. I can play it again. Midpoints, and I can do it one more time. Here's one last line segment, and here's the final point on the curve. It's a beautiful picture, right? A beautiful construction. That's all you need to understand. You only need to put this picture in your notebook, and then the rest is just the same. It's just expressed in a different language. Now, what is the curve? The curve will look like this. Okay, that's the curve. Now, if you were to move this particular t value, or the t value forward and backward, you would pull this entire configuration forward or backward, right? See that? If you evaluate this polygon for a value 1/4, for 1/4, you would use these points, right? So you would move this whole thing around and you would get a different point. And so, is the principle clear to everyone? Joanna? It's clear?
So to get the remaining points on the curve, you use different values?
You use different values, exactly. So here's my t, right? There's an infinite number of t points between 0 and 1, and you choose how many you want. Say you want 5 points on the curve. If you want 5 points on the curve, you have to evaluate it for 0, for 1/4, for 1/2, for 3/4, and for 1, right? And you plug into that algorithm, into this double loop, you plug these different values in there, and you will get 5 points. This is 1 point. You will get this point, the beginning point, you will get the last point, and you will get a point for 1/4, and you will get a point for 3/4. So now you have 5 locations or parameter values on the t-line that correspond to 5 points on the curve. If you want to do more, well, you use more points and you get better and better resolution, better and better approximation of that shape. Right? And then all these points ultimately on the screen are connected by line segments again, because that's all you can do on the screen, right? Just line segments. Is this all clear? Gary? Garrett? Clear? Oh, the algorithm is to evaluate the curve for a particular value of t. Okay, you are given the points, you are given a t value, and you want to find the point on the curve. This value is the point on the curve for the value t. That's what you're after. Should I try one more time? Okay, I will explain that one more time and make it very simple and use different language to explain it. Okay, so what goes into the algorithm? Into the algorithm takes points as input. Okay? This is part of the input. The other input for the algorithm is one particular value of t. So here's a t line, and you pick one value. This value is a particular value, call it t tilde. And so there are points, and there's a parameter value t. These points are always understood to be connected in this way. And then you say, I want to map this configuration onto these line segments. Always map this on there to get that point, to get that point, to get that point. And you connect this again. You do this game again. You take this ratio, 2/3 to 1/3, and map it here. You get that point, you get that point. You connect and you do this again. You get that point. So this is the last point that you get. This point depends on the original circles and on the value t tilde. And I want to know how I get this particular point, which I just called P, at the particular value of T tilde from the original circles. That's it. And the algorithm does it. So the algorithm takes as input B0 up to Bn and the value of T tilde. This is the input, that's the input, that's the input. And what comes out, this is what comes out. Okay. And now you want to do this for multiple values of T. So you plug a bunch of different T values in there. And then you get a bunch of different points on that curve, on this parabola.
Of this algorithm for what?
To evaluate.
Evaluate for what the for graph or for some feature that you want to imagine.
The application is a designer wants to sketch a shape. Okay? You want to get a shape that looks like this. You want to design something like that. Okay? You don't know the formula for that. There is no formula in your mind. So therefore, if you want to design something like that, you should not start with clicking, click, 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 click on the screen. You can't do that. Your hand is wiggling, right? Your hand is way too, you wiggle around. You can't do that. But you have this notion of shape. You want to have something that looks like this. Okay? On a higher level, you would say, I want a shape that looks like this. That's the shape you want, right? Up, down, up. Okay? So all you do is, you have a sketch, you say up, down, up. And then the computer takes this polygon, evaluates it for a bunch of T values and gives you that shape. Okay? So, meaning, you want to have a shape like this. That's your goal, to get a shape like that. But you do not want to click 1,000,000 points with your hand. All you are interested in, that you want to have up, down, up behavior. So all you click is you click this point, you click, and you click, and you click, and then the computer generates this curve for you. Make sense? Okay.
So this is our method for the splines, cubic spline.
We are not this is also related to splines, so we can't do that too. Okay. All right. So this method I described so far is a geometrical approach to Bezier curves, right? I sketch a polygon and the point comes out and a beautiful curve is being drawn by the computer. There is also an analytical approach to the definition of these Bezier curves. You can say a Bezier curve is defined by some formula. Curve equals a sum of control points times some certain polynomials, and I go to that now. That is an alternative way to describe Bezier curves. Bezier curves defined by so-called Bernstein polynomials. Bernstein polynomials. So that's the important part. So when you read many textbooks, you will just find this definition, and it's very cold and non-geometrical and non-intuitive, but we understand it. So a Bezier curve of degree n is defined as and then there is a formula, C curve, depending on a parameter t, curve of t equals a sum of our Bezier control points, b sub I from 0 to n, they are always n plus 1, from 0 to n, multiplied by certain Bernstein polynomials, times b sub I super n of t. Okay. Now, what don't we know? We do not know what these Bernstein polynomials b sub I are, so we have to define them. Where where b, I, n, I from 0 to n, are the so-called Bernstein polynomials of degree n. Are the Bernstein polynomials of degree n comma defined as b sub I super n of t equals n choose I times 1 minus t to the n minus ith power, n minus I times t to the ith power. Okay. And I also should say that t is running between 0 and 1. That's an alternative to defining and explaining. What's the explanation here? Defining a Bezier curve. This is very cold. There's no picture, right? That's the definition. Now, for the computer, that's good enough, right? The computer only needs to be given these points, the control points, and the computer needs to spit out or compute the point on the curve for a value of t between 0 and 1. And the computer needs to compute these values of these capital B polynomials, right? Defined like that. So the computer can do that. But we don't understand what's really going on geometrically, so that's why I started with the geometry. The geometry is intuitive, right? We understand it, and it's beautiful. This also is beautiful, if you like to think more abstractly. It's a matter of choice, right? So we have to understand this a little bit. We have to understand these Bernstein polynomials more detailed. These Bernstein polynomials, what are they? Okay. Let's compute some of them here. So, as said, these BINs are n choose I times 1 minus t to the n minus I power times t to the ith. What are these? What is n choose I? Do you remember that? What that number is? N choose I? What is that guy?
N minus I factorial times I factorial.
Right. Those are binomial coefficients, right? You remember those things? That was, what was this structure? You remember that? Have you heard about that structure? Pascal's triangle? These numbers are the so-called binomial coefficients, right? Binomial coefficients. Again, it's very hard to understand how these Bernstein polynomials relate to the shape of the curve. So why don't we just draw or compute? I just give you a bunch of Bernstein polynomials over here. Some examples. I just compute some of those for you. Some examples. Okay. Let's see. Here, okay. So here is our direction of t, and I always assume that we are running between 0 and 1. The simplest one are Bernstein polynomials of degree 0. So the simplest one is just a constant 1 function. Okay, so this is the Bernstein polynomial V0, 0 of t. This guy, it is constant. It is constant 1. That's it. Okay, now the next functions are linear functions. So the next Bernstein polynomials are lines, or linear polynomials. And this guy is called B01 of t. And it turns out that this guy is B11 of t. I mean, I first start making pictures, and then I give you the definition in terms of the actual polynomials. And this is, again, 0 and 1. Now I give you the quadratic polynomials. The quadratic polynomials, there must be 3. And they look like this. First one goes down. Second one looks like this. And last one goes up. Those are 3 quadratic polynomials. And this one is called B02 of t. This one is B12 of t. And this guy is B22 of t. Okay, so we have 3 curves, or 3 polynomials. Now in the case of, this was n being 0. Here we have n being 1. Here we have n being 2, 2 meaning quadratic. And here now we have n being 3, 3 meaning cubic. So there we get 4 curves. And they look like this. Here's one. Here's one. Here's another one. And here's one. That's the way they look like. 4 curves. And the first one is called B03 of t. The next one, this guy, is called B13 of t. This one is called B23 of t. And this one is called B33 of t. Now I can also give you the actual definition of these guys in terms of the polynomial expansions. So let me write this down just for the fun of it. B00 is something. Here we have B01 and B11. Here we have B02, B12, and B22. And here we have the functions B03, B13, B23, and B33. Now what do you have to do in order to write the functions down? These, well, you have to compute them according to the definition, right? The definition. A Bernstein polynomial is defined as, and then you just have to use these binomial coefficients and so forth. And we just do this in our head, and we can do this very quickly, right? You just remember this formula, you multiply it out, and then you write it down. So the first function, obviously, is just 1. Huh? The next one is B01, is 1 minus t. And B11 is t. Okay. Now, B02 is 1 minus t squared. B12 is 1 minus t times t, and then the binomial coefficient is 2 in front of it. And the last polynomial is, of course, t squared. And the cubic ones, what are they? They have to be 1 minus t cubed, 1 minus t squared times t, and then the binomial coefficient is 3. Then it has to be 3 times 1 minus t times t squared, and the last one has to be t cubed. And all I did was I multiplied the definition. I multiplied it out. Okay. How did I do that so fast, so quickly? There must be some kind of pattern, right? Some kind of pattern that I use. I cannot memorize these things. At my age, can no longer memorize things. At my age, you only have to think in terms of patterns. So there's some kind of pattern there. What's the pattern? So this is just a remark. There's a pattern there. And we go back to these cubic Bernstein polynomials. Why was I able to do that so quickly, right? The polynomials look like this, going down, going up, and then there's this other guy going up. The next one looks like that, right? And this one was B0, 0. This one was B1. Oh, this was B0, 3. This was B1, 3. This was B2, 3. And this guy was B3, 3. How did I compute them so quickly over there, right? This is the lower right entry over there. How did I do that so quickly? Well, let me tell you how I did that. B0, 3, B1, 3, B2, 3, and B3, 3. Okay. Are what? Okay. The first thing is I use this entry in my Pascal's triangle, 1, 3, 3, 1, and put these numbers in front of the polynomials. Okay, that is that row of binomial coefficients times, and then I do something else. Then obviously I have these 1 minus t terms, 1 minus t, 1 minus t, 1 minus t, times t terms, times t, 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 t. And then there are powers, right? Something I have done with those powers. The initial 1 minus t starts with the power of 3, and then it goes down from cube to square first 0th power. So this power goes down. The other power goes up. This is t to the 0th, t to the first, t to the second, and t to the third. Okay, this is just spelling this out. Here are the binomial coefficients. And here are just combinations of 1 minus t and t, where one of the powers starts at 3 and goes down to 0, and the other power starts at 0 and goes up to 3. That's the pattern. So this column, again, are these binomial coefficients. So that means you do not need to memorize the Bernstein polynomials. You only have to remember the scheme. That's it. So for 1 degree higher, you would start at 4, go down to 0, start from 0 and go up to 4. And the coefficients here would be 1, 4, 6, 4, 1. Right? Make sense? Is that clear, Joanna? Makes sense? Okay. But I personally have to say I only talk about this Bernstein polynomial notation because it is in the textbooks. Okay, you have to, when you see a Bernstein Bezier curve is defined as follows, boom, you only see this formula. This is what this formula means. Okay, but I started first by just showing you the polygon, right? How you take a polygon and do linear interpolation, stuff like that. That's more intuitive. Here's no picture, right? This is just very analytical. So there is a geometrical approach to Bezier curves, which I personally like, and then there's the analytical approach to Bezier curves. Whatever you like, whatever is more intuitive to you is the best version for you, right? I want to talk about a few properties about these curves, and then answer any question that you may have about this topic. Properties. There are three most fundamental properties of Bezier curves. Properties of Bezier curves. Okay. Let's do this and let's follow our intuition. Do you follow your intuition often, or for us? Yeah? Let's follow our intuition. I give you, don't copy this yet, okay? This is not a property. This is just our collective thinking. What can happen? I give you a polygon, and I say the Bezier curve that is implied by this polygon is this curve, correct? No, it's not correct. Okay. Okay, so that's not correct. This is a polygon. I say the Bezier curve implied by this polygon looks like this. Correct? No, not correct. What am I missing? Well, some properties, right? What are some properties of these curves? Huh? Tell me. It connects the last, definitely. So that's the thing. The Bezier curve will definitely coincide with the very first and very last control point, right? Huh? So that's very important. That is called endpoint interpolation. Endpoint, these are the end control points, right? End control point interpolation. And that means that when I take a Bezier curve C and I evaluate it for 0, I get the first B0 control point back, right? And so here's my T line, and I again do everything between 0 and 1. So when I evaluate it at 0, I get the first control point, and when I evaluate it for the parameter value 1, I get the last control point, Bn. Okay, this is endpoint interpolation. So therefore, that means the curve passes through the very first and the very last control point. Okay. Now, another important property. I say the curve will look like this. This is obviously a curve that satisfies that, right? Is this correct? Is this a Bezier curve? No. Why not? It's outside the triangle. Yes, you're getting at it. It's outside the triangle. Okay, you follow your intuition and you say, well, Bernd, the way you have talked to us about this repeated linear interpolation thing, the curve probably resides somewhere within this triangular region, right? Right? That's your intuition. And I tell you that intuition is correct. The curve is somewhere in there. Well, it is this curve, right? The real curve looks like that. We know that already, right? We have registered that. Okay? So the curve is always inside some kind of region, right? What kind of region? The convex hull. You've read the book. You learned it a year ago. Okay. So it lies inside the convex hull. This triangle, given 3 points, the convex hull of 3 points is a set of all points that I can combine in a linear fashion in the plane. And that set of points is all the points in this triangular region. So it has to lie in this triangular region, which happens to be the convex hull of those 3 points. I don't have time to write it down formally, but let me do another example. So for the cubic case, I give you 4 points, right? 4 points. Where is the curve? The curve has to lie inside the convex hull of the 4 control points. What is the convex hull of these 4 control points? Follow your intuition. The convex hull is this region here. Okay. That region consists of all the points that I can write as a linear combination, more precisely as a convex combination of these 4 points. You can write this down too. It's in the book. So the curve has to be a subset of that 4-sided region. Now, I can do another one. I can take 4 points like that, right? 4 control points, 1, 2, 3, 4. And the curve will look like this, right? Here is this shape that I will get. And the convex hull of these 4 points is this region. So the curve lies inside these 2 triangles, right? So this is very good to know that, right? So I know that my curve will never deviate by a lot from my polygon because it always is forced to stay in the convex hull. So that is property number 2. It's called the convex hull property. Convex hull property. And very important, that means a Bezier curve lies inside the convex hull of its control points, inside the convex hull of its control points. If it lies within the convex hull of its control points, it also lies within a more general region. From 2 implies this, implies number 3. 3, a Bezier curve lies in the bounding box of its control polygon, lies in the bounding box. Bounding box of its control polygon, or control points, better. Okay, a picture for that. What does that mean? Again, I give you 3 points. What is a bounding box of 3 points in computer graphics terms? So here is the coordinate system, right, x and y. The bounding box considers the x minimum, x maximum, y minimum, and y maximum values. That's the bounding box. So the bounding box is from here to here and from here to here, right? So the curve has to lie inside that bounding box, right? This is, call it x, the x min line, x min. This is x max. This is the y min line. And this is the y max line. Why? Because the bounding box is a superset of the convex hull, right? This would be the convex hull, but the bounding box is a little bit larger than the convex hull. So therefore, if the curve is in the triangle, it also lies in this larger square, right? Why is this important? It comes in the next lecture, why that's important. It has to do with intersection. Wherever you want to intersect things, we have to make sure that, well, there is a test that tells us whether something can intersect or not. If the bounding boxes of things, of curves, intersect, then there's a chance that the curves intersect. If the bounding boxes do not intersect, then maybe the curves don't intersect, right? Does that make sense, Sam? Okay, good. Any questions before I finish? Any questions about this? All of this has to be very clear to you. This is the foundation for everything that follows. I know some of you had this in 175 and so forth. This is pretty easy for you. It's just a refresher. But for this course, this is the basis and everything follows from that. For us, makes sense? It's good? It's okay? Clear? All right. And let me tell you again, this Friday there will be a discussion section. And Sohail will be leading that, and you will be seeing a nice video showing you what I did on board in still form, in movie form, okay, in animated form. So everything that I did on the board in stills, Sohail will show you in a computer animation. Much more pretty. Bye-bye.
The preceding program was brought to you by UC Davis on iTunes U. Please visit us at itunes.ucdavis.edu.